In learning a science subject, I always recommend the first thing to do is to get clear your definitions, to know that what the jargon means, to know that what the terminology means. So get it out of the way. Everyone agrees on the same definition before you start talking. Never has something been more true than, for example, the jargon work done in physics. This is another word that is potentially very confusing to a lot of beginner physics students. It's because it does not mean what you think it means. When we say we do some work in daily life, there's some relation to work done, but we have a very specific meaning. And we'll talk about positive and negative work done. In daily life, you struggle to understand what is a negative work done. If I do negative work, what does that mean? And don't try to wreck your brain. Think about it mathematically. I'll give you the definition. If that number, so this equals to something times something, if that number comes out negative, it's negative. End of story. So that's kind of, so at some point, whenever you find it confusing, detach yourself from any daily life meaning of work. Just like in everyday life, we misuse words all the time, right? Weight and mass, we talked about that in the previous video. When you buy an apple, you say how much does it weigh, but what you mean is how much is it, what is the mass? Because you measure things in kilograms, not in newtons. Anyway, so that's just one of the few examples where physics is guilty of using everyday life words differently. The way I see it, there's two choices. If you want to invent a rigorous term, you have two choices. Either use a simple word and define it properly and then use it that way. That's sort of the physicist approach. The other way is what I call the biologist approach. You invent a different jargon. That could be a word that is completely not in common daily usage. Well, that's good and bad on both ways. So you'll never confuse if I have a word like photosynthesis, right? Then no one is going to confuse that other than a biological process, right? Then some daily use. But if you call that absorbing light and turn that into energy or whatever, if I invent a more concise word than that, then it's slightly easier to understand. I mean, photosynthesis is kind of a common word, at least to a scientific person nowadays. But if you imagine you're a kid, the first time you heard of it, you have completely no idea what that means, right? So it's not intuitive at all, but it's very precise. The other way to do it is to tell you, oh, that process is called absorbing light. Well, it's very intuitive, but then it's not very precise because someone would go like, oh, okay, so the moment I go out to the beach and sunbath, right, then I'm doing photosynthesis. No, you are not a plant. So there's pros and cons with that. Physicists kind of take the one way of doing it is let's use the everyday word. So it sounds intuitive and it's good. So we avoid spelling words that's longer than 7 letters. Every jargon we have is within a couple of word limits. So that's good. So you don't have to learn complicated words. But the bad is be careful, right? We actually do mean something rigorous, just like any biological terminology or chemical terminology, specific meaning to it. It's just something you have to get used to, and something it's good to know off the bat. I've pointed out one trickiness over here is energy is tricky to define because precisely of what I said. You can either make it intuitive, in that case it's not very precise, or you can make it precise but not very intuitive. I'll tell you what that means, because in any textbook, sort of the textbook definition of energy is called the ability to do work. Okay, so, or capability to do work, ability to do work. If you type a quick Google, what is the physics definition of energy, you see everyone says it's ability to do work or the capacity to do work or the potential to do work. I'll try to avoid use the word potential, since potential energy means something specific as well, but it's that idea. So energy, so the definition requires you to know what does do work means. So what is the amount of work done? So now work done, in my opinion, the best way to understand work done is the intuitive way, not the precise way, but the intuitive way is the amount of energy required to overcome a force. Now, can you see the problem? Now it's circular, because to understand work done, you need to understand energy. To understand energy, you need to understand work done. So that's what I think it's the intuitive issue over here. On the formal side, there's no circular reason. There's no circular reasoning happening. And on the formal side, this is defined as basically force times displacement. Okay, so in words, it's the amount of force applied over a certain displacement. Think of it as distance at the moment. You know the difference between distance and displacement. But so just for the intuition, think of it as the amount of force applied over a given displacement. Okay, so think of this as distance. So if you apply some force over a certain displacement, a certain distance, right? Push something, then you have done work. Okay, so it seems intuitive, but then what if I apply the force on the positive x direction and the displacement is negative? Then you get negative work done, and that's where all the complicated things come about. And I'll tell you the in equation form. Oh, also very important. Let me do this in red. Is whenever you say work done, be careful. There's a fine print over here. It's work done is always on something by a force. Okay, it's on something by a force. Just like force is always on something by something, right? On a test object by a source object. Just like gravity, the gravitational force, right? It's on a test mass by a source mass. Right? So remember, whenever you say force, never just say force. It's force on A by B. Okay, right? So if I ask, hey, what's the force on the rock? That's an invalid question. That's meaningless. Sometimes when people say, well, what's the force on something, they kind of mean what's the net force on something. That's fine. What that means is what they really mean, if I translate that, is what's the total or what's the net force on something by everything else. Okay, there is still a by, but it's just in parentheses, in brackets. It says by everything else. That's what net force means. So when you say what's the force by something, on what, you need to specify that, right? Unless it's sometimes we're lazy and we understood it and then we don't read this out, we don't write this out, but always think whenever something is confusing, ask yourself on what by what. Okay, that's for force. Same thing with work done. It's on an object of interest by a force. Okay. Now in equation form, you'll see why I don't like this way of defining it is because it's complicated. Work is defined as the dot product between the force vector from initial to final and integrate that from initial point to final point with the dr. How complicated is that? There's first an integral, and there's also limits to the integral. There's vectors inside, and there's a dot product, which we haven't discussed yet. So we have discussed how to add, subtract. The most advanced things we did was take a scalar like lambda, or it's a simpler scalar like k times a vector. All right, so that just stretches the vector v by k units. All right, if this is a fraction, then you shrink it by many units, etc. So we understand that. But what does vector times vector mean? What does that mean? We haven't discussed that yet. If you take this arrow and times this arrow, what does that mean, right? We know how to add it. We don't know how to multiply it yet. So we will talk about that because it's part of the course in every physics journey. But I don't think it's the good starting point. Okay, so this is the textbook definition. I think there's a better way to do that, which is both more intuitive and also precise. Okay, so I'll write this in blue. Is the ability to change an object's kinetic energy. Okay, now you might think this is a cop-out because then I'm defining energy in terms of energy. No, not really. I will define what kinetic energy means. And kinetic energy is very simple. Okay, kinetic energy is defined as 1/2 times the mass times its speed square. Okay, so remember when you write things in equation form, make sure you define each variable. So KE is kinetic energy, sometimes just K if I'm being really lazy. That's the mass of the object of interest, and V is the speed. Notice we can't square vectors. We don't even know how to multiply vectors, let alone square. So whenever you see V squared, it means speed. Okay, it doesn't mean, so it's the magnitude of that squared, the speed of the object. So kinetic energy is a measurement of its speed. All right. So I'm not defining energy in terms of energy. It's just happened. This is called kinetic energy. I could just replace that and say the ability to change an object's half mv squared. Okay, so we know I'm defining a new word in terms of old words, right? We know what mass is. Mass is the measurement of inertia. It's how much a force resists acceleration. Mass is defined as the proportionality constant of that, of force and acceleration. Remember, force is proportional to it. So this is the proportionality constant. It's interpreted as how much it resists a force for a given acceleration. And velocity, we know it's a change in displacement over change in time, okay, the time taken. So I'm defining new words in terms of old words. There is no circular reasoning going on. If you don't like the fact that it's called kinetic energy, call it rocket, whatever, right? It's the ability to change an object's rocket. But yeah, so right. So now you might think, well, then is that a little bit of call out as well? So are you defining energy in terms of something else you need to define? Well, that's the same thing with the textbook definition. It's the ability to do work, and then you need to define what is work. With my definition, it's ability to change an object's kinetic energy, and I define kinetic energy. The benefit is this is much more intuitive. It's also rigorous. I'll show you in a second. It's also rigorous, right? But this is more intuitive. When I say it to ability to change an object's kinetic energy, you can basically visualize it as if the mass does not change, then you can slash velocity. So energy is the ability to change an object's velocity. Okay, so here's an example. If I put an object yay high and put an object this high, right? Which one has more ability to change its velocity? So if I both release them starting at initial speed of 0, right? So release them at rest. When they get to the ground, which one has more ability to change its velocity? Well, both will change. When it comes here, you will have a speed larger than 0. You will have another speed larger than 0 over here. But which is V prime larger or V larger? V prime is going to be larger. This is going to be at a higher speed when it strikes the ground. So this guy has more energy initially, right? Initially, it has more energy because it has more ability to change the velocity. Whereas here, the ability to do work, you go like, well, the ability to apply a force over amount of displacement, depending on how you feel, I don't feel very intuitive after that, okay? Now, the next question is the blue definition, do you lose anything with using the blue definition other than the black definition of energy, right? The answer is no, and I'll prove that to you. It is both rigorous, so remember, this is work. And in one dimension, I'll just do it in one dimension. So there's no worry about dot products and stuff like that. It's just that, okay, from initial to final. Okay. All right, so proof. Proof that both definitions are equivalent. Okay, so we will start with Newton's second law because we are trying to understand motion, right? Okay, so what do I know about Newton's second law? Any force will cause, any net force will cause an acceleration, but let's say an object only has one force on it. Okay, so it'll accelerate. Okay, so what is acceleration? Acceleration is dv dt, and f, f is just f. Now, let me multiply that by a small amount of distance it moves. So if it moves a distance of dx, Now, don't think of that as any derivative. It's just a small distance of dx. If you like, call that delta x. Okay, it changes from here to here. Okay, so I'll multiply that by dx. This is all scalars. Multiply that by dx. And I'm going to add everything up and do an integral. Okay, so if I integrate this like this, so I can do the same thing on both sides because this is the power of equality. If something is equal, you can do the same thing on both sides. And I want to integrate it. Basically, integrate is it's basically the idea of summing many times. Okay. And I'm going to sum it from an initial state to a final state. Okay. So you recognize, first of all, the mass hopefully doesn't change throughout the motion, so you can pull that out. And here, you notice there is a dx dt. And dx dt just means velocity. And this side is exactly the definition of work. Okay. And now, what is integrate v dv? Well, it's half v squared. So I have half mv squared. However, I need to do it from initial to final like this. Okay. Because it's a finite integral. So now when you plug it in, you have final minus initial. Okay. So I've called this kinetic energy. So that's the final kinetic energy minus the initial kinetic energy. It's the same as work. Okay. So if you know how to do calculus, that will make sense. Make a good sense to you. If you're a bit shaky on the calculus, don't worry too much. This is the rigorous proof that change in kinetic energy is work. And there's a name to this proof. These 1, 2, 3, 4, 5, these 5 steps, there's a name to this, and it's called the work energy theorem. Says if you do some amount of work, you will change an object's kinetic energy. So what does that mean? So that means that means doing work over here. Doing work is the same as changing an object's kinetic energy. All right. So in a test and an exam, either way, you'll get full credits for defining what energy is because, as you can see, it's mathematically equivalent. Okay. If you're a bit shaky on your calculus, don't worry about this. The key takeaway is that they are the same. Okay. And I'm just saying if they're completely the same, mathematically equivalent, right? Mathematically equal, then you can use both. But just in my preference, one is more intuitive than the other. Okay, so we're going to talk about a couple of the concepts of how to what is it. So this is on the formal side. What is the definition? And then we'll see. What is the benefit? Is our life any better by learning something new? This is always a question you want to ask, right? Instead of just learning things we're not memorization machine, we're problem solvers. So we want to see how is this new concept going to benefit us, and how is it going to change our way of looking at the world?